This video will be about two other systems in equilibrium. We'll look at dissolving and solutions in equilibrium, and then also how to calculate given the fact that pressure affects equilibrium. So first off, when we talked about dissolving, we talked about the two processes of dissociation and hydration, right? So we put our salt in, the ions fall apart, but this is actually an equilibrium system that as soon as they dissociate and they're moving around and bumping into each other, they may reprecipitate out, right? They may recrystallize. We've seen this, again, we did it with the borax crystals. I've talked about rock candy before, where you can do it with sugar. So essentially, dissolving is a very reversible process. They dissociate and fall apart, but they can also reprecipitate. And in an unsaturated solution, we would say that they're in equilibrium, right? But it's really at that saturation point where we see the perfect equilibrium, because you can no longer dissolve any more than that. Right, if you put more in, the stuff you put in might dissolve, but it would reprecipitate out something else that's hidden. So there's an actual equilibrium here for the process of dissolving. So how we calculate for dissolving is the same as we would do for any other chemical process. You would write a dissociation equation. So the thing you're putting in is the solid, and it's going to dissociate into its ions. And then you write a K expression for that. We call it Ksp, because it is the equilibrium constant for the solubility products. So when you dissolve something and make products from dissolving, those are your solubility products. And then when you multiply them together, you get the solubility product constant, the equilibrium constant for that scenario. Now this is a normal K expression, right? I include my two ions because they're aqueous. I do not include my compound because it's a solid. So we can write K expressions for dissolving using dissociation equations, but instead of calling it an equilibrium constant, we call it the solubility product constant because it's for the process of dissolving instead of a chemical reaction. In order to calculate these, essentially we get all of our information about the solubility product constant from the solubility of that compound, from that number that we dealt with on those graphs, where it was like that max amount that could be dissolved in any given solution. We get all of our data about our Ksp from that information. Okay, so we use the concentration of the ions dissolved at that point to solve for Ksp, because Ksp is for a saturated solution. It's the max amount. So Ksp actually tells us the max amount of ions that can be dissolved for that ionic compound. Right? If we were unsaturated, if we weren't at max, if you stuck those into your K expression, that would give you Q, the reaction quotient. But the problem is this term solubility and solubility product constant. One of the hardest things for most people for Ksp is simply determining what all the terms mean. So here's a small diagram that may help you differentiate. Ksp, again, is a constant. It's a unitless number. You get it by multiplying together the concentrations of the ions dissolved. The solubility can give us the concentrations if we convert solubility into moles per liter. Okay, so there's a relationship here, right? And we'll use ice tables just like we were doing to help you solve these. But that's the new concept. You would get a K expression from dissociation. So that dissociation equation, again, comes back to being important for us because that's how you get the K expression. And in class, we'll actually work on doing ice tables and calculating with Ksp. The last equilibrium constant that we're going to look at in this unit is for pressure. So we talked about how for Le Chatelier, both concentration and pressures affect equilibrium. Well, so then you can calculate equilibrium constants with pressures instead of concentrations. Now, these equilibrium constants are not equal. The equilibrium constant based on concentration is not the same value as the equilibrium constant for pressure. But because gases are easier to measure pressure than concentrations, we often talk about the equilibrium as it relates to pressures instead of gases. And the equilibrium expression here is the exact same as what we've been doing for concentration, right? Products over reactants, or right over left. But instead of using the brackets and the concentration, you just name it as pressure. Okay, so the K expression for gases using pressure have all these pressure labels. So I'm going to do an example to show you what this looks like, and then obviously we'll deal with the math in class. So for the equation on the board, on the screen, we see that they're all gases. And so if I wanted to write the equilibrium constant, and I would specifically say the equilibrium constant related to pressure for you guys, like on a test or whatever, what that would look like is it would be a Kp instead of a Kc, and then it's still products over reactants, but again, instead of the concentration of NOCl, it'd be the pressure of NOCl, and I would still square that because of its coefficient, and that would be divided by the pressure of NO, and that would be squared, and I'd multiply that by the pressure of Cl2. So I still have three variables, just like I would get from a Kc expression, but now I'm doing pressures instead of concentrations, still raising them to a power of their coefficients. So what we would plug into these locations would be a pressure number, an ATM or a kPa, in order to solve for the Kp. Again, Kp is not the same thing as Kc, it's a different equilibrium constant. So now we have Kp, we've got the K for concentration, which is what we've been doing, and we've got Ksp, which is always the ion product, or the products of the ions in any given dissolving. So those are your three. We'll do math on these after this. Go ahead and do the form and have a nice night.